waves. So in this problem, we see that we have two quantitative variables. One is the sea surface temperature, which is recorded in degrees Celsius, but instead of having a 0, which is your usual freezing water temperature, the 0 here represents the temperature at the end of the 20th century. This is a common approach for climate change analysis. The other variable is global wave power in megawatt per centimeter. And we have data for each year. So that means that in our scatter plot, any one point, like the one in the upper right corner, represents the data for one particular year. So on this one particular year, for the tallest point in the graph, the sea surface temperature relative to the late 20th century was 0.2, so 0.2 degrees higher than the late 20th century. And that year, global wave power was roughly 3.2 megawatt per centimeter. We see in this scatter plot that the pattern of those dots makes a generally linear trend. So we can indeed create a linear regression model for it. We see that the pattern is positive and fairly strong. Based on the graph alone, we can approximately compute some of those values that would make up the regression line. So for example, we can find the value of the y-intercept. And for that, we have to remember that the y-intercept is the value of y when x equals 0. So that means we need to first locate x equals 0 on our graph, which in this case happens to be in the middle roughly of the horizontal axis, and then project that onto the regression line so that we can then see what's the equivalent value of y at that point. And we can see that the value of the y-intercept is roughly 2.6 megawatt per centimeter, which is the value of y on this straight line when x is equal to 0. Likewise, you could roughly calculate the value of the slope based on this graph. The slope as a rate of change represents how much does y change for any particular change in x. So pick any two values on the x-axis and then measure the corresponding difference in y. Obviously, you will want to use software to obtain the actual equation for the least square regression line to also calculate how strong this relationship is. So we see that from Crunchit, we get an equation for the fitted line, the least square regression line, which is our variable y, global wave power, equals the constant 2.606, that's the y-intercept, plus 1.804 times our x variable sea surface temperature change. So 1.804 is the slope. Separately, we can obtain the value of the correlation coefficient R using the correlation function. And this gives us an R value of 0.8613. In a linear relationship, the slope, as this rate of change, tells us how much y varies for some change in x. And therefore, specifically, when the change in x is equal to 1, then the change in y is equal to slope times 1, and that's just equal to the value of the slope. Because we're interested in the variable y, for which the points are not perfectly aligned, then we can say that the variable y changes by the value of the slope on average when the variable x changes by an amount of +1 in the units recorded. So very importantly here is to understand that the units of our variable x is degrees Celsius. So we're not talking about tick marks on a graph. Again, tick marks on a graph are an arbitrary choice. So therefore here, what we can say is that for any increase of 1 degree Celsius in sea surface temperature, the global wave power changes by the value of the slope, so 1.804 megawatt per centimeter on average. Now, the correlation coefficient is positive, 0.86, and that's because we have a positive upward linear pattern. And that's a fairly strong value because the correlation varies between -1 and 1, and the closer to 0 it is, the weaker that pattern is, that linear pattern is. So 0.86 is quite strong. Another thing that we learned from this value is that if we square it, we obtain the value r squared, which in this case is 0.74, then this value r squared tells us how much of the variability of the y variable can be accounted for by this regression model. So that means in this case, we can see that global wave power varies a lot from year to year, from a low of about 2.2 megawatt per centimeter to a high of about 3.2 megawatt per centimeter, and lots of variation overall. But if we express global wave power as a function of sea surface temperature change, then the amount of variability around that regression line, so all those residuals, is much smaller. And what R squared tells us is by how much have we been able to reduce all that unexplained variability. In this case, that's 74%.